Hello and welcome. If you're getting ready for your Operations Management C215 OA exam, you're in exactly the right place. I know that feeling of looking at a mountain of material and wondering how to conquer it. But I promise you, by the end of this video, you will have a clear, confident path to mastering these concepts and excelling on your exam. We're going to cover the quality management, statistical control, process control, capacity planning, and facility location. Before we dive deep into our first major concept, I want to let you know about something that's going to be incredibly valuable for your exam preparation. I've created over 300 completely free practice questions that work hand in hand with everything we're covering in this comprehensive guide. You'll find the link in the description, and I really encourage you to bookmark it because these questions will help you apply every concept we discussed today. So let's dive right in. Let's begin with the absolute bedrock of modern operations: total quality management, often shortened to TQM. Before we can manage quality, we have to agree on what it even is. Think about your favourite coffee shop. What makes it a quality experience? Is it that the latte always tastes exactly the same? That's called conformance to specifications. Is it that the coffee successfully wakes you up in the morning? That's fitness for use. Is it that you feel the $2 cup of coffee was a great deal? That's value for price paid. Or is it the friendly barista who remembers your name? That's support services. Or maybe it's just the cool, relaxing vibe of the place and the logo on the cup. That's psychological criteria. For your exam, you need to know these 5 ways to define quality inside and out. Let's look closer. Conformance to specifications is the engineering perspective. It's about meeting preset targets and tolerances. An iPhone screen must be manufactured to within a tiny fraction of a millimetre of its design. If it is, it has high quality in this dimension. Fitness for use is the user's perspective. It asks a simple question: does this product do the job I hired it for? A cheap $5 hammer from a discount store and a $50 professional hammer are both fit for the use of hammering a nail, but they are designed for different users and levels of use. Third, value for price paid is purely subjective and resides in the customer's mind. A student might find a $1 pen that writes smoothly to be a high-value, high-quality product, while a business executive might feel a $100 pen offers better value due to its feel and professional appearance. Fourth, support services is about everything that happens after the sale. A car company that offers a great warranty, easy-to-schedule service appointments, and a helpful roadside assistance program is delivering high-quality service, even if the car itself is just average. Finally, psychological criteria is all about perception. It's the prestige of a luxury brand, the feeling of safety associated with a certain airline, or the ambience of a high-end restaurant. It's intangible but incredibly powerful. It's also crucial to understand the difference between manufacturing quality and service quality. Manufacturing quality is tangible. You can touch it, measure it, and manage it directly. We can measure the durability of a sneaker, the reliability of a laptop, and the number of features on a new smartphone. Service quality, on the other hand, is intangible. It's an experience. It includes consistency, like a fast food chain delivering the same burger everywhere. It includes responsiveness, like how quickly a hotel responds to a request for more towels. It includes courtesy and friendliness, like the attitude of a call centre agent. And it includes the atmosphere, like the lighting and music in a retail store. The key takeaway is that managing service quality is often more difficult because it's highly subjective and depends on individual perceptions. So why do businesses obsess over this? Because quality, or the lack of it, has a huge financial impact. This brings us to a critical exam topic: the cost of quality. Imagine this simple phrase: an ounce of prevention is worth a pound of cure. That is the entire philosophy behind managing the cost of quality. These costs are broken into 4 categories, which fall into 2 main groups: control costs and failure costs. Let's think of this like building a house. Control costs are the money you spend proactively trying to make sure the house is built right the first time. The first type is prevention costs. These are the best kind of costs. This is the money you spend to prevent defects from ever occurring. In our house analogy, this is the cost of hiring a good architect to create a solid blueprint, the cost of training the construction crew on the latest building codes, and the cost of planning the project carefully. In a business setting, it's employee training, quality planning, and process design. The second control cost is appraisal costs. This is the cost of checking to see if things are going right. It's the cost of measuring and monitoring. For our house, this is the money you pay a building inspector to come at various stages and check the foundation, the framing, and the electrical work. In business, this includes the cost of testing products, performing quality audits, and inspecting incoming materials from suppliers. Now for the second group, failure costs. This is the pound of cure, the money you spend when things go wrong. The first type is internal failure costs. These are the costs of defects that you catch before they leave the factory and get to the customer. It's a failure, but at least you caught it in-house. In our house analogy, this is when the carpenter cuts a piece of expensive crown moulding too short and has to throw it in the scrap pile. Or when the painters realise they used the wrong shade of white and have to spend a day repainting a room. It's the cost of scrap, rework, and downtime. So why do businesses obsess over this? Because quality, or the lack of it, has a huge financial impact. This brings us to a critical exam topic: the cost of quality. Imagine this simple phrase: an ounce of prevention is worth a pound of cure. That is the entire philosophy behind managing the cost of quality. These costs are broken into 4 categories, which fall into 2 main groups: control costs and failure costs. Let's think of this like building a house. A great way to remember these 4 costs is the acronym PAF: prevention, appraisal, internal failure, external failure. On your exam, you will absolutely get scenario questions asking you to classify a cost. Remember, if it's proactive and meant to stop problems, it's prevention. If it's about checking or inspecting, it's appraisal. If a problem's found before the customer gets it, it's internal failure. If the customer finds the problem, it's external failure. Before we go any deeper, I want to let you know about something that will be a huge help as you prepare for your exam. I've put together a bank of over 300 completely free practice questions that are designed to work perfectly with the concepts we are covering today. You can find the link in the description below. I highly recommend you open it and bookmark it now, because applying these concepts is the key to mastering them. The ideas of TQM didn't just appear overnight. They evolved. The old concept of quality, say from the 1950s, was very simple. Inspect for quality after production is finished. You'd have a factory churn out thousands of widgets, and then at the very end of the line, you'd have a team of inspectors who would sort the good ones from the bad ones. This is incredibly wasteful and expensive. The new concept of quality, which is the heart of TQM, is to build quality into the process itself. It's about making it impossible to make a mistake in the first place. This philosophy is driven by several core principles. First is an unwavering customer focus. The goal is to identify and meet customer needs, because they are the ultimate arbiters of quality. Second is continuous improvement, a concept perfected in Japan and known as Kaizen. It's the philosophy of never being satisfied. It's about making small, incremental, ongoing improvements to every process every single day. A key tool for this is the PDSA cycle. Plan, Do, Study, Act. Let's use a non-business example. Say you want to improve your study habits for this exam. You plan to study for 30 minutes every day. You do it for 1 week. You study the results. Did your practice quiz scores improve? If yes, you act to make this a permanent part of your routine. If not, you go back to the planning stage and try something new. This creates a cycle of constant learning and improvement. Another key TQM principle is employee empowerment. This means giving the people who actually do the work the authority, responsibility, and tools to identify and correct quality problems themselves. This often involves a team approach, such as quality circles, where a group of 8 to 10 employees from the same area meet regularly to analyse and solve work-related problems. To empower employees, you must give them the right tools. This brings us to the famous 7 tools of quality control. For your exam, you need to know what each tool is, and more importantly, when to use it. First is the cause and effect diagram, also called a fishbone diagram or an Ishikawa diagram. It's a brainstorming tool. Imagine a pizza delivery place is getting complaints about late deliveries. The effect is the late pizza. The team would brainstorm potential causes and group them onto the main bones of the fish, such as people, driver got lost, process, inefficient route planning, equipment, oven not hot enough, and materials, poor quality pizza boxes that fall apart. Second is the flow chart. It's simply a picture of the steps in a process. It's great for visualizing the process to find bottlenecks, redundant steps, or points where errors are likely to occur. Third is a checklist. This is a very simple form for collecting data, often with just tally marks. It's used to track the frequency of events, like the number of times a certain type of defect occurs per day. Fourth is the control chart. We will discuss this in great detail soon, but for now, think of it as a process heart monitor. It tracks a process over time to see if it is stable and predictable. Fifth is the scatter diagram. This is a graph used to see if there is a relationship between 2 variables. For example, a factory manager might plot the humidity in the factory on one axis and the number of paint defects on the another axis to see if higher humidity is causing more defects. Sixth, and very important for your exam, is the Pareto analysis. This is based on the 80/20th rule, which says that in many situations, roughly 80% of the problems come from only 20% of the causes. A Pareto chart is a special type of bar chart that shows the causes of problems in descending order of frequency. Imagine a restaurant gets 100 complaints in a week. 70 are for cold food, 15 are for slow service, 10 are for wrong orders, and 5 are for rude staff. The Pareto chart would make it visually obvious that the most important problem to solve, the vital few, is the cold food. Finally, we have the histogram. This is a bar chart that shows the frequency distribution of a set of data. It can tell you at a glance if your data is centered on a target value and how spread out it is. A tall, narrow histogram is good. It means your process has low variability. A short, wide histogram is bad. It means high variability. What we just covered about TQM philosophy and the 7 tools is a perfect example of the kind of conceptual knowledge you'll need for the exam. To make sure you can apply it, head over to the free practice question bank I mentioned. You'll find questions that give you a scenario and ask you to choose the best tool for the job. Now let's transition from the philosophy of quality to the mathematics of quality with statistical quality control, or SQC. SQC is just a fancy term for using statistical tools to evaluate quality. The most important branch of SQC for your exam is statistical process control, or SPC. The entire idea behind SPC is managing variation. Every single process in the world has variation. If you sign your name 10 times, each signature will be slightly different. SPC recognizes 2 types of variation. The first is common cause variation. This is the natural, random, background noise variation that is inherent in any process. It's predictable and unavoidable. The second type is assignable cause variation. This comes from a specific, identifiable, and correctable cause. For instance, a worn-out machine part, a new and untrained employee, or a bad batch of raw materials. The whole purpose of SPC and its main tool, the control chart, is to help us distinguish between these 2 types of variation. This brings us to the control chart, one of the most important concepts in the entire course. A control chart is simply a graph of some data plotted over time. It has 3 key lines. A center line, which represents the historical average of the process, an upper control limit, or UCL, and a lower control limit, or LCL. It is critical that you remember this. These limits are not the customer's specification limits. They're calculated directly from the process data itself, and are typically set at plus and minus 3 standard deviations from the center line. Here's how it works. As long as the data points you plot fall randomly between the UCL and LCL, your process is considered to be in control. This means that only the normal, common cause variation is present. The process is stable and predictable. However, if a data point falls outside the control limits, or if you see a non-random pattern of points inside the limits, like 7 points in a row all going up, this is a signal that the process is out of control. It's a red flag telling you that an assignable cause has likely entered the process, and you need to stop, investigate, and fix the root cause. There are different control charts for different types of data. This is a huge topic on the exam. You need to know which chart to use when. The first type of data is variable data. These are things you can measure on a continuous scale like weight, length, temperature, or time. For variable data, you must use two charts together, an X-bar chart and an R chart. The X-bar chart monitors the central tendency, or the average, of the process. The R chart monitors the range, which is a measure of the dispersion or variability of the process. You need both because the process average could be perfectly on target, but the variability could be increasing, which the R chart would catch. Or the variability could be stable, but the process average could have shifted up or down, which the X-bar chart would catch. The second type of data is attribute data. These are characteristics that you count, typically in a yes, no, or pass-fail format. For attribute data, we use P charts and C charts. A P chart monitors the proportion or percentage of defective items in a sample. For example, if you are inspecting samples of 100 light bulbs to see how many don't work, you would use a P chart to track the percentage of defective bulbs over time. A C chart is different. It monitors the number of defects per unit. You use this when a single item can have more than one defect. For example, if you are inspecting newly made dining tables, you could use a C chart to track the number of defects, scratches, dents, paint drips, found on each table. To make this simple for the exam, ask yourself this: am I measuring or counting? If you're measuring, you use X-bar and R charts. If you're counting, you have one more question. Am I counting the number of defective items or the number of defects on one item? If you're counting defective items, it's a P chart. If you're counting the number of defects on a single unit, it's a C chart. I know this can be a lot to absorb, especially the different chart types. This is another area where working through the practice questions I've provided will be incredibly helpful. You'll see various scenarios and get practice choosing the right chart, which will build your confidence for the OA. Now, for a very important distinction that trips up many students. A process being in control is not the same thing as being capable. A process can be perfectly in control, meaning it is stable and predictable, but it might still be producing 100% junk that doesn't meet the customer's needs. This brings us to process capability. Capability is all about whether your process can meet the specifications set by the customer. These specifications are also called tolerances. They have an upper specification limit, USL, and a lower specification limit. Think of it this way. Imagine you are trying to park a car in a garage. The width of the garage door opening represents the specification limits. The width of your car represents the natural variation of your process. Process capability analysis answers two questions. First, is your car physically narrow enough to fit through the garage door opening? Second, are you a good enough driver to park it in the middle without scraping the sides? There are two key measures for this, CP and CPK. CP is the first and simpler measure. It answers the question, is my car narrow enough to fit through the door? It is the ratio of the specification width, the garage door opening, to the process width, the car's width. If CP is greater than 1, your car is narrower than the opening, so it has the potential to fit. If CP is less than 1, your car is wider than the opening, and it will never fit, no matter how good a driver you are. The big problem with CP is that it assumes you park the car perfectly in the centre every time. But what if you don't? This is where CPK comes in. CPK answers the second question. Am I actually parking it without hitting the sides? CPK also measures the process capability, but it crucially takes into account whether the process is centred. It looks at the distance from your process average to the nearest specification limit. Therefore, CPK will always be less than or equal to CP. If they are equal, it means your process is perfectly centred. If CPK is smaller, it means your process is off-centre and is drifting closer to one of the specification limits, increasing the risk of producing defects. For your exam, this is a critical distinction. CP is about the potential of your process. CPK is about the actual performance. A CPK of 1.33 or greater is often considered the gold standard for a capable process. This relentless drive to improve process capability and reduce variation is the core of Six Sigma. Six Sigma is a business management strategy that uses data and statistical analysis to improve performance and eliminate defects. The name Six Sigma refers to a statistical level of quality so high that it allows for only 3.4 defects per million opportunities. It's about achieving near perfection. The structured methodology used to execute Six Sigma projects is an acronym you should know, DMEC. It stands for Define, Measure, Analyze, Improve, and Control. You define the problem. You measure the current performance to get a baseline. You analyze the data to find the root causes of the problem. You improve the process by implementing solutions that eliminate the root causes. And finally, you control the new process to make sure the improvements stick. It's a highly rigorous and data-driven version of the PDSA cycle we discussed earlier. If some of these more advanced statistical concepts like CPK and Six Sigma feel a bit challenging right now, please don't worry. That's completely normal. They are some of the toughest topics in the course. The best way to solidify your understanding is to see them in action. The free practice question bank in the description has worked examples that will take you through these calculations step by step. Now let's shift gears from the nitty-gritty of quality controls to the big picture strategic decisions of capacity planning and facility location. Capacity is the maximum output rate of a facility. It's how many cars a factory can produce, how many patients a hospital can treat, or how many customers a restaurant can serve in a day. Capacity planning is the process of establishing the output rate that can be achieved. This is a massive strategic decision because capacity is expensive. It's purchased in large, indivisible chunks, and it's a long-term commitment. There are two important ways to measure capacity. Design capacity is the maximum possible output under absolutely ideal conditions. Think of a pizza oven that could theoretically cook 30 pizzas an hour if it were running non-stop with no delays. Effective capacity is the maximum output rate that can be sustained under normal, realistic conditions. This accounts for things like employee breaks, machine maintenance, and scheduling mix-ups. Our pizza oven's effective capacity might only be 20 pizzas an hour. We then measure capacity utilization, which is our actual output divided by our capacity. If our pizza place is currently making 22 pizzas an hour, its utilization relative to its effective capacity is 110%, meaning they are in overtime and pushing hard. Its utilization relative to design capacity is about 73%. When planning capacity, companies are driven by the search for the best operating level. This is the level of output that results in the lowest average cost per unit. Initially, as a company increases output, it experiences economies of scale. The cost per unit drops because fixed costs, like the factory rent, are spread over more and more units. But if a facility gets too large, it can suffer from DICE economies of scale. The cost per unit starts to rise again due to problems like congestion, communication breakdowns, and increased complexity. Making a capacity planning decision under uncertainty can be daunting. A powerful tool to help is the decision tree. A decision tree is a diagram that models a decision, showing the different alternatives, the chance events that could happen, and the potential outcomes. Let's walk through an example from the slides very carefully. A restaurant owner needs to expand. She can expand small now or expand large now. The decision is represented by a square node. If she expands small, there are two possible chance events, represented by a circular node: high demand with a 70% probability or low demand with a 30% probability. If demand is low, the payoff is $80,000. If demand is high, she reaches another decision point. She can choose to expand again for a payoff of $200,000 or not expand for a payoff of $150,000. To solve a decision tree, you must work from right to left. Let's start at that second decision square. The choice is between $200,000 and $150,000. You'd obviously choose the higher number, $200,000. So we prune the $150,000 branch and carry the $200,000 value back to the chance node. Now we can calculate the expected value, EV, of that chance node. The EV is the weighted average of the outcomes. So we have a 70% chance of a $200,000 payoff and a 30% chance of an $80,000 payoff. We calculate 0.70 asterisk $200,000 plus 0.30 asterisk $80,000, which equals $140,000 plus $24,000 for a total EV of $164,000. This is the expected value of the expand small decision. You would then calculate the EV for the expand large decision and choose the one with the higher number. This is a very common type of question on the OA. Finally, the decision about how much capacity to have is directly linked to where to put it. This is facility location. There are many factors affecting this decision, like proximity to suppliers, customers, and labour. But for the exam, you'll need to know the quantitative tools used to compare locations. The load distance model is one. It helps you choose a location by calculating a score that minimises the total travel distance, weighted by the number of loads being shipped. You calculate the distance between a potential site and each of your destinations. You then multiply each distance by the number of loads going to that destination. Finally, you add up all these values to get a total load distance score. You do this for each potential site, and the site with the lowest score is the winner. A related tool is the centre of gravity approach. This method is used to find an ideal starting point for your location search. It calculates the geographic centre of all your destinations, but it weights the coordinates of each destination by the number of loads it receives. It gives you the X and Y coordinates of a location that is the theoretical ideal for minimising travel. You would then look for an actual, available site near those coordinates. As we bring this comprehensive session to a close, let's take a moment to see how all these pieces fit together to form the big picture of operations management. Think of it like a pyramid. The broad, strong base of the pyramid is the philosophy of total quality management. It's the belief that customer satisfaction and continuous improvement are the foundations of a successful organisation. The middle layer of the pyramid is the toolkit of statistical process control. This is where the philosophy becomes action. It's the control charts, the process capability analysis, and the Six Sigma methods that allow us to measure, control, and improve our processes with data-driven precision. And at the very peak of the pyramid are the high-stakes strategic decisions like capacity planning and facility location. These decisions can only be made effectively because they rest upon the strong foundation of a quality philosophy and the solid, data-informed processes beneath them. Your OA exam will test your ability to move between these layers. You'll need to know the TQM philosophy, be able to apply the statistical tools, and understand how they inform strategic choices. You've covered a tremendous amount of ground today, and you should feel proud of that. The key to cementing this knowledge and walking into your exam with confidence is application and practice. Go back through these concepts, especially the ones that felt tricky. Use the analogies we discussed, like parking the car in the garage for CPK, to make them stick. And most importantly, work through as many practice problems as you can. Don't forget to use that link in the description to access the 300+ free practice questions I've created for you. There is no better way to prepare for the OA than by tackling questions that are designed to be just like the real thing. With the deep understanding you have built today, combined with dedicated practice, you're putting yourself in an excellent position to succeed. Thank you for your time and focus. Good luck with your studies and go ace that exam.